Hi everyone, welcome to the tutorial. Today we're going to be taking a look at how to access the LLC90 dataset, which is hosted on SciServer, and then also take a look at an example of how to use OceanSpy to carry out model data comparison with observations. So to get started, we need to make sure that we have our tutorial notebooks in the right SciServer folders, and these are hosted on github.com/hingroup/oceansciences2022. Now we can just simply either download these, or if you're familiar with Git, then you can go to the folder in SciServer and then simply clone the repository. So let's move on to SciServer, and at this point we've already made a video of how to make an account on SciServer and how to get access. So I'm assuming you already know how to do that. I'm going to go ahead and log into my own account, and this is the SciServer dashboard. So we want to now move on to using the compute application on SciServer and create a container. So I'll name my container LLC90 tutorial for the time being. And here are two main things that you need to keep in mind when you're creating a container. The first thing is you want to make sure you have the right compute image. For our purposes, it needs to be Oceanography 2.3. This basically means that it's the right Python environment, which has most of the updated Python libraries. And the second thing that's important is that you select the right data volume. LLC90 right now is hosted under the ocean circulation data volume, which is what we're going to be selecting. And in the next video, when we take a look at LLC4320 data, we're going to be using the Poseidon data volume. So we can go ahead and create this, and it takes a few seconds to generate our container, and then we can simply go ahead and look at what the Jupyter environment looks like. It's always good to switch to the Jupyter Lab environment. So this is where I'll try and introduce you where you need to run and store the files that were present in the GitHub repository. You want to go to the temporary folder, and this is where you'll have a folder with your username on it, and you go into Scratch, and this is where you basically want to store your files. So since I've already done that, I'll just go ahead and open the notebook, and this is what it looks like. So before we get started, I'll just make sure that we restart the kernel, clear all outputs, and now I can get started with reading the LLC90 dataset using OceanSpy. So the first thing we need to do is simply import some of the packages and do some bookkeeping. At this point, you don't really need to create a DOS client, but I'm still going to do it because we'll take a look at how big the dataset for the LLC90 is, and then how does it scale with the LLC4320 dataset. So it's always a good practice to know when and when not to use DOS. For the purposes of this tutorial, I'm going to go ahead and create a DOS client though. Now this is where we basically take a look at how to access the Echo dataset, which is the LLC90 dataset. We have a functionality in OceanSpy, which is called Open Ocean Dataset, and we have several data catalogs which are hosted on SciServer, one of them being the Echo dataset. It takes a few seconds for OceanSpy to read that. This data is hosted in a ZAR format, so it takes just a few seconds to essentially read this, and we'll take a look at how big the data set is, which is just 145 gigabytes. So this is a relatively small size of a data set. Keep in mind that the Echo data set that's hosted on SciServer is generated in a way that it is able to conserve most of the heat, salt, and volume budgets, and that takes about 145 gigabytes. We'll go ahead and then take a look at what this actually looks like. So the LLC90 is basically the grid of the Echo dataset, and it's divided in a way that the dataset has 13 faces or tiles, and each tile has a 90 by 90 grid with 50 vertical levels. And we can take a look at what the coordinates of that dataset looks like, and also what are the variables that eventually are imported in the Echo dataset. For somebody who's familiar with the Echo dataset, you already know what these variables look like. If not, it's always helpful to get familiarized with the Echo dataset. Moving on, we'll first get started with using the OceanSpy cutout function, and this is where we start using OceanSpy very seriously. So the reason we want to use the cutout function is twofold. One is the function of the cutout function is it makes or it transforms the LLC grid into a approximate regular lat-long grid. So it converts all of the 13 tiles / faces into a grid which doesn't have these faces and simply has the data stored in latitude, longitude format. And the other thing that it does is that it helps in selecting a regional cutout of the dataset. So in this case, once we select what the variables we need for this simple analysis, we take a look at just temperature and salinity. And now we provide an X and a Y range to the cutout function. And you can also provide what the Z range is and what the time limits are for our cutout. And you can provide all of those arguments into the cutout function, which is subsample.cutout. And it takes a few seconds to do that. We can then take a look at how big the data set looks like once it's transformed using a cutout. And it's about 56 gigabytes, which is a relatively easier chunk of data to work with. And how does it look like? It looks like a transformed data set. We don't see any faces or tiles anymore. We simply have a transform grid into X and Y, basically, lat and lon. And this is where we can now, once we have the transform data, take a look at how to now compare certain sections from observations with the Echo dataset. So for the purposes of this tutorial, we're going to take a look at the A1 and the A5 section in the North Atlantic as described in the WOS stations. So this is where it's important to note that you have your test data folder also in the same SciServer Scratch environment, because we already have downloaded certain files from the CCHDO, the repository for A1 and A5. You can go ahead and use Xarray to just simply read those. And once we do a little bit of cleaning up of the Echo data, we can now take a look at what it takes to create a section in a model output using OceanSpy. And it's as easy as writing a function calling a function which is subsample.surveystations. And the arguments for that function are basically the longitude and latitude and depth, which is basically the same as cutout. And the way that we do it is because we already have our observations, we simply read the lat and lon from those observations and provide them to the survey stations function. And once you do that, you can create these artificial survey stations which recreate these ship-based measurements. And OceanSpy does that pretty quickly, and the OceanSpy object that you get is also very small in magnitude. So now we want to make sure that we have the right sections. So we're going to go ahead and visualize how these sections look like, what the domain looks like essentially in the model once we create these artificial sections. And we can do that also by using a plotting functionality in OceanSpy. There's a plot horizontal section function in OceanSpy where you just need to provide the variable name, and then you can also provide other arguments that are needed, which are essentially car-to-py arguments. And so this takes a couple of seconds, and then we can look at the domain, which looks like this. So we have the A1 section in the subpolar North Atlantic, and we have the A5 section, which essentially is the rapid section. So we know that these are artificial sections which have been now recreated in Echo, and they look exactly how the observation sections look like. And at this point, we can simply go ahead and plot the salinity and temperature between the Echo data and the ship-based measurements. And all I'm doing in this cell is creating a subplot between the observations at the top and using the plot function of OceanSpy to plot a vertical section, which is at the bottom. And the interesting thing about this plot is this is where you realize, the utility of OceanSpy in creating these artificial sections. Because the Echo data is on a 1-degree grid, the resolution of the topography is essentially the same, and so it's actually difficult to ascertain which one is observation and which one is model data unless you take a closer look at it. So this is for the OB line, which is basically the A1 line, and this is the salinity vertical section. You can go ahead and play around with this cell and also plot for the A5 section. We do the same thing for temperature, and we notice for A5, if you take a look at, the same thing happens. You can't really differentiate a lot between the model and the observations because of similar resolution sizes. And you can, go ahead and do further statistical analysis if you want to compare more objectively how these two data sets compare. You can also play around with the cell to take a look at the A1 section for temperature and perform other analysis that you would want to do. And so with this, we come to an end of this tutorial, and I would highly encourage people to go ahead and play around with OceanSpy functionality and see if you can do more with it. In the next tutorial, we're going to take a look at the LLC9320 dataset and how you can do similar things and more with OceanSpy in it.